Jnanam paramam dheyam. Knowledge is supreme.
So let's try to write the Sx and the sigma x as the next step using the experimental data. We have written Sz assuming the up state is an eigenstate of Sz and down state is an eigenstate of Sz with the eigenvalues as plus half h cross for the up state and minus half h cross for the down state. Okay. In the same eigenstate of Sz, we would like to write the Sx operator and Sy operators. And we know that those operators should be such that it should be traceless. If we try to find the eigenvalues, since it splits into two beams, the eigenvalues of those states should be again plus half h cross or minus half h cross. All these data we know, but we still have to find what is Sx. How can you go about it? One is to use this property and try to figure out what is the 2 by 2 matrix which will satisfy this, and you can figure it out. Other one is to use logics using the Stern-Gerlach apparatus and try and figure out what is Sx and Sy with these stringent conditions. They have to be traceless, eigenvalues have to be of the sigma x and sigma y have to be plus or minus 1. Okay. You can use various methods and try and figure this out. Okay. So, what is the operator form for Sz for spin half is the question. Just look at only the valence electron that we get two states with eigenvalues Sz equal to plus half h cross and Sz equal to minus half h cross. We denote symbolically as an up spin for the eigenstate of Sz with eigenvalue plus half h cross, and similarly down to denote eigenstate with eigenvalue minus half h cross. Sz operator in the above basis, you can write up state and down state the corresponding dual vector as a row matrix, row vector, and you can work it out. Will Sx also be diagonal in the same representation? No. That we know because they are incompatible observables. Go back to the Stern-Gerlach sequence of measurements which we did, and what do we say? That the Sx eigenvalue is plus half. I am suppressing the h cross now, let us not worry about it, you can put it back later. Sx equal to plus half h cross, after you make it go through the SGX, the state with plus half will be a superposition, in general will be a superposition of the two basis states. Okay. Experimentally, we saw that it was equal intensity. So, we are going to put the magnitude as 1 over root 2 and 1 over root 2. We want to normalize the states. There could be a theoretical phase factor here which will not be experimentally detected, but you can in principle have a relative phase factor. Overall phase factor is useless, but you could have a relative phase factor. So, this is the most general state, one of the eigenstates of the Sx operator can be written. The other eigenstate should be orthogonal to this state. The Sx equal to minus half will again have equal intensity, but the coefficient should be such that those two states are orthogonal, and also that state per se should also be normalized. In fact, I could have put an up spin here and a down spin here just to make notation simpler, but you know both the notations. Okay. Similarly, the other eigenstate, as I said, I put a negative sign here so that they will be orthogonal, and use the eigenvalue equation for the Sx operator. What is the eigenvalue equation for the Sx operator? Same, similar to what you had for the Sz states, but now it should be eigenstates of Sx operator. But these eigenstates are not eigenstates of Sz operator. That's why we wrote them to be a superposition of Sz states. Use this, and using this data, I want you to fix what is the matrix form or the operator form for Sx. I'll leave it to you as an exercise. Do it and check it out. The 4 elements in the 2 by 2 matrix. Please try to work it out the way I did it for the sigma z using these equations and the previous data. These 2 data you use, and using these 2 equations try to figure it out what should be the matrix representation or the operator representation for the Sx operator. It is off diagonal matrix. Please verify. After you have done that work, you can verify whether I get this with these appropriate phase factors. Okay, so this is an outer product of the up, down, and similarly down, up. How will you write the matrix for this? Sx is up, down with e to the power of minus I delta h cross by 2, and then you have a plus h cross by 2 e to the power of plus I delta down, up. So what will this be in matrix form? H cross by 2, I will take it out. Diagonal is 0, right? Off diagonal is the other way around or this way. So again traceless. What about the square of these matrices? 1 or eigenvalue is plus or minus 1 for this matrix. Check it. Call that matrix as sigma x. Find what this is. Find eigenvalue of sigma x. Okay. So as of now, I have not fixed what is delta as he was asking. We could have chosen delta equal to 0, but we will do it systematically. I want you to verify this. This I have not worked it out, but please do it yourself and check it. Okay. So similarly, instead of putting it through SGX, you put it through SGY. Instead of SGX, if you had put it through SGY, then an arbitrary eigenstate, the same argument. There will be 2 eigenstates for SY operators, and you can write the states of SY operator again as a superposition of SZ eigenstates with a different phase factor. Let me call it as delta prime. Okay, so I can do that. Write it as 1 over root 2 times SZ equal to plus half h cross plus e to the power of I delta prime by root 2 SZ equal to minus half h cross. I can do this. The way I wrote it for the Sx states in terms of the eigenstates of Sz, I can also write Sy states in terms of the eigenstates of Sz. And do the same things the way we did and fix what is the Sy operator. Again it will be up or up down with some coefficient, with another coefficient, down up. Okay. What are those coefficients? Fix it by using the same arguments. If I had an Sy operator on Sy equal to plus half H cross, it has to be plus half H cross on Sy equal to plus half H cross, and plus half H cross state is this. Rewrite it and try to find the matrix element in the basis states of SZ. Do you all understand, right? Will you do it? Again you will find a matrix for this, which is very similar to what you did for your Sx, but only delta will replace it by delta prime. So now to determine the phases delta and delta prime, we can also do the superposition, the Stern-Gerlach, first along x and then along y. Again you will have equal intensity. So the superposition of an Sx state, there will be equal components of Sx equal to plus half and minus half in a specific Sy state or vice versa. So that means the probability should be equal. Use this fact and try and fix what is delta and delta prime choices. Show that the norm or the, it's not norm, the inner product of two states will be this, and the mod of that should be 1 over root 2. And similarly, the inner product with the Sy equal to minus half and Sx equal to plus half is this. And now you fix your choice. What is the possibility which will fix this choice? Delta minus delta prime has to be pi by 2. Is that correct? So that's it. Once I get delta minus delta prime to be pi by 2, I can now make a choice. Let's take the Sx eigenstate to have no phase factor. Put delta to be 0. Then because of this property, I have to make the relative phase for the Sy operator to have delta prime to be pi by 2. There is no option. Yeah, plus 1 minus pi by I pi by 2 doesn't really matter. So with this, if you try to write the matrix operator for Sx and Sy, so there is no phase factor here, but here you will have a minus I and plus I. Okay. But this, as you are pointing it out, it could have been a plus I and a minus I also. It doesn't violate any of these properties. But only thing is you have to make sure that your Sx Sy commutator is Sz, and then one of the signs will be conveniently done. Okay. So write the matrix form for the Sx and Sy and figure out what is sigma x and sigma y. Can you write it down? Matrix form for the Sx operator, if you try to write, this will be half H cross sigma x. Note that each of them is Hermitian. This I, blindly if you write I and I, it won't be Hermitian. Sigma y. They are traceless, eigenvalues are plus or minus 1, and they have the properties that sigma x squared is identity, sigma y squared is identity. You can also check what is sigma x, sigma y. What is sigma x, sigma y? I times sigma z. Very good. So you get this minus I, and if I do that, that is 0, then I, so 0 with an I, and that you can write it as I, you can take it out, minus I, you can take it out, and 1. So there is a slight notation here. If I put this to be minus I and plus I as sigma y, and then you get I times sigma z. So this is one unique convention which is taking care of this, and it will take care of your algebra Sx Sy commutator should be IH cross Sz. Okay. So 0 minus I 0 is what we will call it as a sigma y. So the sigma x, sigma y, sigma z in any textbook if you start seeing, they are called the Pauli matrices. Sigma x, sigma y, sigma z are called Pauli matrices. Okay. What are the properties? Sigma x squared, sigma y squared, sigma z squared is identity. Trace of sigma x, trace of sigma y, trace of sigma z is 0. Sigma I, sigma j is I times sigma k with an epsilon ijk, sorry, epsilon ijk I times sigma k. Is there an I or it's not there? It's there, right? This is a compact way of writing what I wrote for sigma x, sigma y is I times sigma z. You can write sigma I, sigma j as epsilon ijk I times sigma k. Can I write further? If I and j are equal, sigma I, sigma j is delta ij times identity. If I and j are equal, and if I and j are not equal, which is epsilon ijk, I times sigma k. Okay. So you can do various other things with these Pauli matrices. If I give e to the I a sigma dot a vector, what is this? It is e to the I sigma x ax plus sigma y ay plus sigma z az. We did this e to the power of I sigma z times some theta. What did we get here? Cos theta plus I sigma z sin theta. You can argue that theta is the magnitude which is oriented along the z direction to start with. And what do you expect from there? Some theta vector if I had, I would have written this as cos of mod theta plus I sigma dot n hat sin of mod theta, where theta vector is just by inspection. You can also verify here using Pauli matrices properties. Use the Pauli matrices properties and try and work it out. What is e to the power of I sigma dot a? It should be cos mod a plus I times sigma dot unit vector of mod a, only the direction. Sigma dot or sigma cross? Sigma dot, right? Please verify some of these things. I'll put it in the assignment also, but please verify that the polymatrices are very rich and it helps you to do many of these things. But why am I doing this exponentials? What is the reason? How did you write the translation operator? When I wrote the translation operator, which shifts by a vector unit, it had an exponential of I, and then you had an operator which I said that the operator is a linear momentum operator, and how much steps you want to translate, that is what you get, is what you had. I also at some point tried to motivate you to look at, for very small rotation angle, what should be the rotation operator. What did we do for the rotation operator? For a theta, if delta theta was very small, it was 1 some minus I theta or plus I theta, and let's do it along z direction, I said. Then what did we have? Lz by h cross. I asked you to look at how the r vector changes under infinitesimal rotation and fix what should be the rotation operator, and you write this. This is for infinitesimal. You can keep continuing. If you keep rotating about the same axis, you can keep continuing exactly like the way we wrote here. What will that be? Exponential of I Lz theta z by h cross will be for r of theta of z. This is rotation in your physical position space. This is rotation in your physical position space. But I have tried to tell you, in the position space you have orbital angular momentum. An experimental Stern-Gerlach experiment tells you that you should also have spin angular momentum. You can also have a rotation in the internal spin space. Okay. So that will be denoted by e to the power of I. Let's do Sz, rotation by theta z by h cross. And what is Sz? Sigma z, half h cross sigma z, right? So that is a by 2 theta z. So this is an operator which will perform rotation in the internal space by an angle theta z. And the by 2 comes because of the explicit representation of the spin operator, or the eigenvalues are half, plus or minus half h cross. That's why this comes. So if I want to write what this is, I have to write this as cos of theta z by 2 plus I sigma z sine of theta z by 2, because of this two factors. So all these polymatrices shows up in rotation in the internal space, and you have to be familiar with it. What is the nature of these operators? Are they unitary? These operators are unitary. You can also say that R is, they are real entries, then you can call them to be orthogonal. So these are in general unitary operators. What is the dimension of these matrices? You can write a matrix representation. This is a 2 cross 2 matrix, right? This is a 2 cross 2. The e to the by 2. So, you can write this as cos theta by 2 plus I sin theta z by 2. Sigma z is 1 and minus 1, right? 0, 0 cos theta z by 2 minus I sigma z. Sigma z is minus 1 times sin theta z by 2. So, what will this matrix be? E to the I theta z by 2, 0, 0, fine? No? That's it. So, there are a lot of manipulation you can do with polymatrices, and the core thing is that these are unitary operators which perform your rotation in the internal space, and they are 2 by 2 matrices. So, these set of unitary matrices, they have some properties, group properties. We will come back to it at some point. So, for you to check Sx operator, Sy operator and check your commutator relation, and from there you put in all the properties of the polymatrices, and we will use them in all our computation for a two-dimensional linear vector spaces which corresponds to this internal spin half space, and you need to have this hands-on feel on playing with these polymatrices. So, that is why I put in this. Okay. So, I stop here.